Alright, so now I'm going to talk to you about real gases. So first, let's talk about what ideal gases were again. So an ideal gas is one that has completely elastic collisions. That means that if one gas bumps off another gas, that it is not going, that the sort of velocity and mass and that kinetic energy that they started with is going to be the same afterwards. If there's going to be no stickiness between different particles of gas. There's also no volume occupied by those gas particles themselves. So for instance, if we've got a container full of gas particles, you'd imagine that those gas particles have no dimensions to them, but we know that atoms do take up space, that they have a nucleus and they have orbitals occupied by electrons. So there is a volume occupied by gas particles. So how do we deal with that, and how does that affect the behavior of gases? Well, one thing that we see with gases that are not ideal, which is every gas, is that at high pressure, the relationship that we see from the ideal gas laws or the other gas laws starts to kind of fall apart. Because if we have a large container and we have these gas particles in here, their volume is kind of negligible. But if we squish all those gas particles together, well, notice how then the proportion of the gas particles volume, or the whole volume of that container, how much that volume is actually the volume of the particles themselves. So as we see pressure sort of increase, this means our volume is usually a little bit more than expected by the ideal gas law. Another thing is when we have decreasing temperature. Basically, real gases deviate from the ideal gas law when temperature decreases, because what is happening when temperature decreases? Or it gets low. Once the temperature gets low, we usually see gases changing state and turning into liquids. Another concern is, and one that I didn't mention here, is that as decreasing temperature, the kinetic energy of those particles is not enough, can't resist attractions between each other. So this also allows things to become liquids. Also, these attractions between particles, if we think about our polar molecules like NH3, which is our ammonia, we know that ammonia is a polar molecule. So those attractions become stronger at a decreasing temperature. But also, if we have these ammonia particles floating around in a container, so there's going to be this force of attraction between those two particles. So if this particle is about to hit the wall, the force that it's going to hit the wall with is going to be less. So the force is less, so that pressure is less due to attractions between air particles. So because we have to consider the volume of particles and we have to consider the attractions between particles, this fellow, van der Waals, came up with this equation, which basically is this, that the pressure plus the number of moles of an atom, and this A and the volume squared times the volume minus the number of moles, and B equals nRT. Some of these variables you're already familiar with. P is still pressure. V is still volume, even though you see it in two different places now. N is still moles, even though you see it in three different places. R is still our gas law constant. T is still temperature. Our new variables are A and B. So A is the attractions, is a constant that, or for the attractions between particles, not a constant. It's the measurement of the attractions between particles, and B is the volume occupied by the gas particles themselves. And these two numbers are numbers that you can find in your textbook as well.